Hello everyone, I'm Chen, a graduate student of civil engineers, and my study track is transportation. Today I will show you a literature review of serverless in the wild, characterizing and optimizing the serverless workload at a large cloud provider. First of all, I need to intro some basic concept to you guys, and maybe most of you are already familiar with this. The function as a service is a software paradigm that is becoming increasingly popular. Multiple cloud provider offers fast as an interface to, to usage-driven, stateless, serverless, background service in fast. Users do not explicitly provision or configure virtual machine or containers. Fast users do not pay for resources. They do not use it either. Instead, users simply upload their code of their functions to the cloud. The function get executed when triggered or invoked by events. The provider is then responsible for the provision the needed resources with high function performance and billing users just for their actual function executions. And another concept is cold start and warm start. Warm start is a function can be started quickly. That means the code is already in the memory, but it has a high cost. On the contrary, the cold start has a long started time. As we can show the picture, see the picture, the cold start contains the download and extract code. The container starts and the runtime bootstrap, and for the warm start, it's just the code execution. A function can be started quickly when the code is already in the memory. So how to pursue a high performance and low cost? The first of all is function or the execution code in the memory. And if we can get the warm starts experience and the cold starts cost, ideally, the provider wants to give the illusion to all the users and all the functions are always warm. But the spending resources is always cold. Third, we depend on the different varying resources needs, triggers, and invocation. We need to decide what kind of resources should keep in the memory. We will talk about this later. And for their strategy, they use a different keep alive value for each user's workload according to its actual invocation frequency and pattern. And they enable a provider in many cases to pre-warm function execution just before its invocation happens. So what about the triggers? As is shown in the fraction of the all functions, and the all invocation per type of the triggers, HTTP is the most popular in both dimensions. Even triggers corresponds to only 2% of the functions, but 24.7% of the invocations. Due to their automated and very high invocation rates, Q trigger also have proportionally more invocation than functions. The opposite happens with the time triggers. There are many functions triggered by time, but they correspond to only 2% of invocations due to the relative low rate they fair in. 95% of the time trigger function in our dataset were triggered at most once per minute on average. So here's the design challenge for them. The first challenge is hard to predict invocations. Prediction the next invocation is very challenging, which when the triggers is not a time trigger. The second challenge is heterogeneous applications. As the picture shows, the invocation frequency and the pattern vary substantially across the application. The third challenge is application with infrequent invocation. They will take up a long time once they are invoked. Same to the application which is first time run. And the fourth change is the tracking overhead. The cost of tracking for the information for each application should be small, but sometimes it's just overhead. And the last one is the execution overhead. Due to those overheads, expensive prediction technologies such as the time series and size cannot be used for the applications. The main takeaways. The first one is the vast majority of functions execute on the orders of the few seconds. Looking at the distribution of this maximum allocated memory, 90% of the application never consume more than 400 megabytes, and 50% of the application allocated at most 170 megabytes. 75% of them has a maximum execution time of 10 seconds. And the second one, the vast majority of applications are invoked infrequently. 81% of them average at the most one invocation per minute. At the same time, less than 20% of the application are responsible for 99.6% in all invocations. Thus, it is expensive in terms of memory footprint to keep the application that receive infrequent invocation resident at all time. The third one, many applications show widely variable, so wide variability in their IETS. 14% of them have a CV of their IETS higher than 1. So the task of predicting the next invocation can be challenging, especially for the applications that are invoked infrequently. They come up with a hybrid histogram policy. Their hybrid histogram policy addresses all of the above challenges. To address challenge 1 and number 2, their policy adjusted to invocation frequency and the pattern of each individual applications. It identifies the application, the invocation pattern, remove and unload the application right after each function executed ends, reload or pre-warm the application right before a potential next invocation, and keep it alive for a period. The pre-warm window starts after the function execution, and keep alive window starts after each pre-warm. If the pre-warm window is 0, we do not unload the application after the execution. And the end of the execution, it will still start a new keep alive window. The policy comprises 3 main components. The first one is range-limited histogram for capturing each application idle time, the ITS. Secondly, the standard keep alive approach for when the histogram is not representative. There are few ITs, or the IT behaviors is changing. And thirdly, the time series focused components for when the histogram does not capture most ITs. To address challenge number 4 and number 5, center pairs of their policy is a compact histogram data structure that checks the IT distribution for each application. Each entry or bin of the histogram counts the numbers of the idle times of the corresponding length that has already occurred. We use 1 minute bin. They use 1 minute bins, which strikes a good balance between the metadata size and the resolution needed for the policy action. Keep, keep alive time, scale in order of the minutes for FISA platform. This figure shows the structure of the open WISC. It, it exposes a REST interface for user interact with the fast platform. For controller, they added a new logic to the load balancer to implement the hybrid policy and update the keep alive and the pre-warm parameters after each invocation. For API, they send the latest keep alive parameter for a function to the corresponding invoker alongside the invocation request. For invoker, they unload the containers based on the keep alive parameters received from the activation message. For their methodology, their simulation processing is use the simulator generating array of the invocation time for each app. And then the simulator infers whether each invocation would be a cold start or not. Then the simulator will keep tracks of when each application image is loaded and aggregate the waste memory time for application. The simulation requires a long execution to assess applications with infrequent invocations and exploring a large space of the configuration. The simulation result. There is a significant cold start reduction going from a 10 minutes keep alive to an hour. Then 75% application experience cold starts and half of the time for 10 minutes keep alive. This number goes down to 25% for an hour. The pre-warming reduces all the waste time significantly. As we can see at the picture, the cost is slight increase in the cold starts. And for the trade-off between the cold starts and the memory wasted as a function of the service threshold using a 4-hour range. The CV means the standard deviation divided by the mean. The cold start improvement is more pronounced in last quarter of the distribution, since application with infrequency invocations are those that benefit the most. They run two experiments with 16 randomly selected mid-range popularity applications from the workload on their 19 virtual machine OpenWhisk deployment. Compare with the cold start behavior of the hybrid the 10 minutes fixed and keep alive policies. The significant cold start reduce follow the same trend with their simulation. On average, and across to the 18 invoker virtual machines, the hybrid policy reduced the memory consumption of the worker containers by 15.6%. The hybrid policy reduced the average and 99% function execution time 32.5% and 82.4%, respectively. This is due to secondary effect of the open risk, where the language runtime bootstrap time is eliminated for the warm containers. And for their conclusion, it is incredible how much of the variation exists in the real-world workload running in the Azusa functions. Across to all the metrics above, there never seem to be one or two dominating scenarios. The second part of the paper uses the data to analyze the potential improvements in cold start of